Hi everyone, welcome back to Dave's Math Channel. I'm your host David Tear, and today I'm going to talk about an important area of math called game theory. And what is game theory? Well, I took this from Wikipedia. I'm not going to go through all this, but simply stated, game theory is a branch of math concerned with finding the optimal strategy for playing a game, a game of competition. And by game, I mean it in a pretty loose sense. I mean, it includes all games of strategy. Like board games and card games. But it also includes more abstract forms of competition that you could also think of as games, like economics, where you have competing companies, or politics, where you have competing nations. So it has a lot of very practical applications, not just for playing games. But anyway, that's what it is. And I'm going to give you a brief history of game theory. So, games of chance were the first type of games to be analyzed mathematically, and this was done in the 16th century by a handful of pretty great mathematicians. Probably the first one was Girolamo Cardano, Italian mathematician who was also a gambler, by the way. And I think one of the reasons he developed this theory because he wanted to know how to gamble better. He liked playing dice games, and he actually invented probability theory as part of how we try to analyze the games we like to play. And I think there were a number of other mathematicians around the same time that did the same thing. And another guy who was interested in games of chance was Christian Huygens. He Both of these guys wrote books on games of chance. The one by Cardano was just called Books of Games of Chance, which he wrote in 1564. The one written by Huygens was called On Reasoning and Games of Chance. That came out just 3 years later, 1567. And then in the 19th century, there was a guy named Cournot who came up with what's now known as the Nash equilibrium, which was named after another famous mathematician named John Nash in 1950. Uh, in modern game theory, most of that was developed by another very famous mathematician named John von Neumann. And he wrote two books on his theory. The first was called On the Theory of Games of Strategy. That came out in 1928. And then he came up with another book with more of a focus on economics, as an implication of game theory. It was called Theory of Games and Economic Behavior. That one came out in 1944. And I think the last thing I should mention on this slide is there's a very important problem in game theory known as the prisoner's dilemma. And this was a problem first discussed by Merrill M. Flood and Melvin Drescher. They both worked at the RAND Corporation, and they came up with this in 1950. Um, uh, anyway, I'll get to that later, but that's just a brief outline of the history of game theory. So let's continue. So there's different types of games, and one way to analyze games is something called a game matrix. And on the left is a very simple example. We have a very simple game called matching pennies. So we're supposed to imagine that we have two players, and I guess one of the players wins if the ends up on heads, the other wins if the coin ends up on tails. And the numbers in this matrix, notice that each entry of the matrix has two numbers in it. And I guess heads we call player one. So if the coin turns out heads and the player who guesses heads guesses right, then he wins. So that's a +1 score. And similarly, if the player who is doing tails wins, if the coin ends up on tails, he gets 1 point. And obviously, if they lose, it's the other possibility where they score -1. So that's just a simple example of a game matrix. There's a little bit more complicated one on the right. I'm not going to go through this in detail, but you see the game possible scores, and once you have this game matrix, you can analyze it, and you can figure out the best possible strategy for these players. And they do that here. I'm not going to go through that in detail, but it's just to show you that you can analyze these game matrices, and come up with an optimal strategy. Um, and there's a particular type of game that's very important, known as two-player zero-sum games. And I guess I have to explain what that means. So the two-player part is easy. That just means there's two competing players in the game. And zero-sum means that like one player wins and the other loses. So if you want to give the game a score of +1 if first player wins and -1 if he loses. So obviously you have one winner, one loser. So the sum of the scores is 0, right? So and they can also both draw. So that's what they mean by zero sum. You sum all the scores of all the players, it gets 0. And there's several examples of games like this. The one I just showed you, Matching Pennies, is an example. Tic-tac-toe is another simple example. And then there's more complicated examples, which are more interesting games, like checkers and chess and Go. And one thing von Neumann did, which was really remarkable, was that he was able to analyze, he came up with an optimal strategy for guaranteeing that any player who plays a two-player zero-sum game, if they follow this strategy, they're guaranteed to never lose. They might draw, but they'll never lose if they follow this strategy. And that's true of all the games I just mentioned, including chess and Go. The reason it doesn't work for those games is because those games involve so many possibilities for those games. Like for instance, chess, I think there's especially there's something like 10 to the 120th power. That's the number of possible games of chess. And Go is even more. I think it's 10 to the 193rd power. So it's completely impractical to use as his strategy for those games because it would take longer than the age of the universe to do that, even with a computer. But I want to kind of give you an idea of how his strategy works. So I'll explain it for a simple game, tic-tac-toe. And what we do for a game like that, we could in principle do this for any two-player zero-sum game. But like I said, since chess has so many possible games, you have to put each possible configuration of the game in one of these nodes of this tree. And then you'd have like 10 to the 120th power nodes for the tree for chess, which is completely impractical, like I said. But for tic-tac-toe, you can do it. I think there's only something like 25,000 possible games of chess, and that's no problem for a computer. So it's pretty easy to write a computer program to play an optimal game of tic-tac-toe that will guarantee that you never lose. And I think just without even a computer, it's pretty easy to play tic-tac-toe. I mean, anybody with just a little bit of experience can play a perfect game of tic-tac-toe where they never lose. But I want to kind of explain how this Minimax works. So first, what you do is you write down the game tree corresponding to the game, which is just a tree with nodes, branches going down to the possible, configurations of the game. The nodes on the bottom indicate the final configuration of the game. So the way the strategy works, say you're X, and they don't actually show the initial configuration. They show a configuration midway through on top. But imagine this is the configuration, the top node. So then what X would do is X turns now, on turn now, X just goes down the path that leads to the highest possible score for X, which is just any branch any path that ends in you want to go down the path that ends in the highest number. So that would be a 1, because 1 just corresponds to X winning. If there's any branches that do lead to a 1, you just go down them. And if not, you go down a path with a 0, But if you've been playing by the optimal strategy, there'll never be a path that ends in -1. And then O does the same thing. So once X takes his turn, then O does the same thing. O wants to maximize his score, which means minimizing the game score if you use a convention that +1 corresponds to X winning and -1 corresponds to O winning. So X's strategy is going to be to try to maximize his possible score, and O is to minimize the possible score. That's why it's called minimax. And anyway, that's how it works in principle. And it doesn't just work for tic-tac-toe. Like I said earlier, it works in principle for any two-player zero-sum game. And like I said, it's not practical at all for chess, but there is a method where you can still use it for complicated games like chess. It's called minimax alpha beta pruning. And I have to explain this a little bit. It's a very, very useful algorithm, by the way. As a matter of fact, it's been used in computer programs for chess for many decades. And finally, there was a computer built by IBM called Deep Blue. I'm sure most of you heard of it. In 1996, Deep Blue became the first computer to ever beat a chess champion. In this case, it was Garry Kasparov, the reigning champion from Russia in 1996. He lost. He was the first champion to ever lose to a computer, and that really made the news. But the way that works, I want to explain the algorithm a little bit. Pruning just means you don't go through the whole tree. You go through a few plies. I think in this diagram they show 5 plies of the tree. And a ply in chess is just half a turn. So, it's like a ply would correspond to white moving or black moving, 1 move. So 2 plies are a turn. And, I mean, the more plies you have in your algorithm, the better the program is. But like I said, chess is such a complicated game, you can't go through the whole game tree, which is usually about 40 moves, which is like 80 plies. You can only go through maybe up to 10 or 20. I don't know how many Deep Blue went through. Probably a lot, probably like 20 or something. But if you go through enough, you can beat any human because humans don't do this. I mean, one thing about humans when they play chess is they don't use this mini max alpha beta pruning in their mind. They only see the good moves, kind of. They know some good strategies, and humans don't really think like computers. But if you have a good enough computer program like Deep Blue, it does use this minimax alpha beta pruning algorithm, and if it's deep enough plies, it can beat any human opponent, which is what Deep Blue did. So anyway, yeah. But like I mentioned earlier, I guess that's enough for games right now. I want to talk about the prisoner's dilemma right now. And this is a very famous problem in game theory, and it doesn't apply so much to just recreational games. Actually, it turns out it was the basis for most of the Cold War strategy, both with the United States and the Soviet Union. But first, I have to explain what it is. So the prisoner's dilemma, the reason it's called that, it involves a scenario involving 2 criminals who get arrested for committing a crime. And what happens is, they both cooperated on this crime, but they each get caught and arrested and separated. And so then what happens is the arresting officers offers each of these prisoners a choice. He says you can either confess to the crime or not confess. And then there's a kind of a game matrix associated with this. So what happens is there's 4 possibilities. Either both criminals confess, in which each one will serve 6 years in prison for committing the crime, or player 1 could confess and player 2 not confess. If that happens, then player 1 well, if player 1 doesn't confess and player 2 confesses, then then player 2 gets 10 years in prison and player 1 goes free, and vice versa. If player 2 doesn't confess and player 1 confesses, then it's the other way around. And finally, if neither player confesses, then each one gets 1 year in prison. So obviously, if you're looking at the whole matrix, the best strategy for both of them would be for both of them not to confess, because then they both just get a year in prison. If they both confess, they both get 6 years in prison. However, this is why it's called a dilemma. That it's if each player is just if each prisoner is acting in their own self-interest without regard for the other prisoner, then what they'll probably end up doing is both confessing. And the reason they will is because whatever the other player does, whatever the other prisoners does, the one who confesses is better off. I mean, look at this. If player 1 confesses and player 2 confesses, if player 2 confesses, he gets 6 years. If player 2 doesn't confess, he gets 10 years. So I mean, he gets nothing. So that it's better in either case for them to confess rather than not to confess, even though it would be better for both of them to both confess. So what do you do about that? Obviously, you want them to cooperate, and this is a lot like the Cold War, if you think about it, because that replaced confessing and not confessing. We had the United States and the Soviet Union, both with a big arsenal of nuclear weapons, I guess enough to destroy the other side. So what did they do? I mean, I guess the strategy was called mutually assured destruction, or MAD. I mean, obviously, neither the United States nor the Soviet Union wanted to launch a first strike because, I mean, I guess that would have been, it's kind of like the prisoner's dilemma. I mean, I guess if we didn't have any regard for the other side, that's what each side would have done, right? Because like if we destroy the Soviet Union, we're not going to be destroyed. Uh, if we didn't do a first strike, then there's a chance that the Soviet Union would have destroyed us, right? But obviously, that wasn't in our best interest. Our best interest was for neither side to do a first strike. So the prisoner's dilemma kind of illustrates that. Yeah, and anyway, I think I explained it in detail already. The last thing I want to talk about is games of chance. And I already mentioned that in the history of game theory. Yeah, that was the one that was developed in the 16th century by people like Cardano. And games of chance are more complicated than deterministic games. Those are games that aren't games of chance, where they're just based on what the players do, not based on any probability of occurrence, like when you're rolling dice or playing cards, right? So anyway, but you can do the same kind of analysis. It's just a little more complicated if it's a game of chance. You have to apply probability theory, and then you get expected values instead of absolute scores based on your move. You get a kind of probability distribution of what your score might be. But you can still analyze it. You just have to replace your scores with expected values, expected scores. And expected values are a pretty basic concept in probability theory. To give you an example, I mean, a very simple example is just tossing a fair coin, which has a 50% chance of landing on heads, a 50% chance of landing on tails. And, if it's a fair coin and you toss it enough times, it's going to be half, gets closer and closer to 50%. But say you just toss it 100 times. It won't be exactly 50%. As a matter of fact, it's pretty unlikely it will be, but it'll be close. And, but the expected value is kind of the average you would get if you did this a lot of times. And since there's a 50% chance of the coin landing on heads each toss, the expected value, if you do it 100 times, is 50. That's the expected number of heads you're going to get. And I guess one last thing I want to mention about this, I don't know if you guys like to gamble on casinos, but one thing you should know is it's pretty easy to prove just using basic probability theory that you are going to lose. If you play any game of chance in any casino where there's no strategy like slots or roulette or craps, you know, then you are going to lose if you play it enough. It's just probability theory. The more times you play, the more likely you are to lose, and the more money you are likely to lose. You might get lucky a few times, but if you play enough, you are going to lose. And that's how casinos make their money, based on probability theory, just a simple idea of expected score, of expected value in that case. So anyway, that concludes this video on game theory. I hope you enjoyed it, and I'll see you next time.